Welcome back. I'm talking to Andrew Johnson about comets. Now, you explained the standard model or the standard theory of comets, that they're dirty snowballs. Now, there's a great deal of contention over this, Andrew. Just to explain why.
Well, I don't think... actually, there's not that much contention in the mainstream scientific thinking. You get a few people who will say, well, these things can't be correct, but again, I was looking when I was doing research for this latest presentation that I was asked to give because of Comet ISON coming into the solar system. I went onto the GCSE Bite Size, the BBC revision website, and it says, comets are dirty snowballs. You get all
of your best research.
Yeah, of course.
You just go straight there. That's
yeah,
all you
that's
need to
right.
know,
Yeah, BBC websites where everything that you need to know is, as we both well know. But that just said comets are dirty snowballs. End of story. That's all you need to. That's all the kids need to know. End of. But again, if you start to explore the actual data that's come back from the probes, and that's been one of the killers for me. I mean, I was familiar with some of this data. For example, you mentioned a few minutes ago about how we've had. I think we've had. We had 3 probes that have gone very close range to comets. One brought back cometary material with a sample and return mission. Another one fired a probe into the head of the comet, and another one flew. Well, it was actually the Giotto probe as long ago as 1986, which flew towards Halley's Comet, and it counted the impact of material before the camera was destroyed by the material being given off by the comet. And they didn't really know at that point what the nucleus was going to be like, and they set the camera to go to the brightest point of the comet. But as they found, the actual surface of the comet was like a dark coloured tarry material, like a bitumen material. Right. Which was a bit of a surprise, because that's not the colour of snowballs. I mean, unless it's a very, very dirty snowball, you'd expect it to be a lighter colour with ice.
So am I right in thinking that one of these probes found that there was way less than 10% water?
Absolutely, and this is one of the things they've tried to sort of couch in different terms. Again, if you look at the... in fact, I've got a good quote here. We'll go forwards to that quote.
All right.
Now, on April the 5th, 2002, we had a NASA spacecraft. It flew past Comet Borrelly, and Comet Borrelly, again, was said to have been described as a dirty snowball, but the headline on the NASA's website says, Comet has hot, dry surface. It has a hot, dry surface, and that's what they found. And it says, Dr. Lawrence Soderblom of the US Geological Survey's Flagstaff, Arizona station, lead author of a report on the Borrelly flyby results appearing in the online edition of the journal Science, said, "We know the ice is there," he said, "it's just well hidden."
Okay.
So what he's basically saying is, we've got data back from the experiment which shows that we didn't see any water, but we're just going to ignore that because we know that we know that it's ice anyway. Right. So that was in 2002, and that was before the Stardust mission. Now the Stardust mission is even more interesting because they sent this Deep Space One probe. This Stardust mission. They sent it to Comet Wild 2, Comet Wild 2, I should say, because it's named after a German guy, and that was in 2004. And that when that got there, the probe was designed such that it collected material which was being ejected by the comet as it was coming close to the sun, and it collected that material in what's called aerogel, which is kind of like a sort of like blue tack, I suppose. And the particles flying off the comet stuck into that, and then they brought that material back in a capsule, and it landed in the desert, and they retrieved that under clean room conditions and everything. And they were able to take that material away and actually do mass spectrometry on it to find out what it was made of. And as is pointed out by the Electric Universe video, which I got a lot of this information from, but it's also on NASA's website. You can go and look at this on NASA's website too. What the particularly interesting thing that they found with the Stardust mission was a material called olivine. Now, that's a mineral which is normally found during volcanic eruption. It comes out of volcanoes, or it's formed during the the process of either a volcano cooling, the lava cooling, or the volcano erupting then cooling, or within the eruption itself. I don't know exactly when it's formed, but olivine is a mineral. And the thing about it is that if you put it into water, in the presence of water, it will degrade. It will change into something else. It cannot form in the presence of water, right? So they found olivine as one part of the material, but then they found other materials which can only form in liquid water, right? They can't form within ice. They can only form in liquid water. And they actually said, after looking at the stardust samples that they got back, that the materials that we found are characteristic of planets in the habitable zone of the solar system. Right. In other words, not from the outer solar system.
Yeah, because if we just consider a star or the sun for a moment, if you go a long way away, it's extremely cold,
right,
and certain chemical things can't happen.
All the chemistry slows down with a lower temperature.
So, all right then. Well, let's just distinguish between elements and compounds.
Yes.
We have the 92 chemical elements that everything's made of.
Correct.
Where are they made first, Andrew?
Well, we're told that up to the elements iron, if you go up in the atomic numbers from 1 up to iron, I can't remember what the atomic number for iron is, but all of those elements are formed during the process of nuclear fusion inside the core of a star.
Right.
So we're told that a star is a nuclear fusion reactor, and all the elements up to iron are formed then. But when you go above iron, they have to be formed by different processes because they can't be formed in a nuclear fusion reactor. And we're told that those elements are formed in supernovae explosions when you have much greater forces of the star exploding, and these elements are then formed during the explosion.
So you have certain elements, and then as they come to within certain temperature regions, you call it the Goldilocks region, certain molecules can then be formed.
Right. Well, that's true. But we're getting then away. We're now into the situation where the star is stable.
Right.
We've got an ongoing reaction of, for example, fusing hydrogen into helium, which is allegedly what's going on in the sun right now, and it gives us all our energy. That's what we're told. And that process then creates heat and light and radiation, and around a star you have planets which can then soak up that heat. There are other chemicals on those planets which then start reacting with each other and form these various compounds, like they form water, for example, from hydrogen and oxygen, and they would form methane, for example, from carbon and hydrogen, and they would form things like carbon monoxide and carbon dioxide. So those are all formed as a result of chemical reactions rather than nuclear reactions.
All right, so tell us what the standard model for comets is, and why the accepted theory suggests that there shouldn't be certain elements and molecules on a comet.
Right, so the standard model is basically that a comet is some bits of dust stuck into a ball of ice. So primarily, according to what they say, is if you were to fly to a comet, you should primarily find ice. When you get there, you crash something into it, ice and water vapor should come off.
And where do they say this ice came from?
Well, they say this ice came from the Oort cloud, because there was a cloud of material left over from when the solar system was formed, and that just contains leftover bits of dust and water, which is hydrogen and oxygen combined. Right. That's the standard sort of model.
Right.
And you obviously you're going to, or according to them, you're going to get things stuck into the snowball, which are just other bits of rock, bits of compounds that formed when the solar system was formed from the whatever process formed it. They get lodged into the surface of the snowball. That gets carried into the solar system when the comet comes around, and so by watching the comet melt, looking at that material, you should be able to tell what sort of materials were there, according to them, in the early solar system.
Right.
So the basic thing we're trying to get to, I suppose, is that it is assumed right down the line that the only thing that comets are a result of is a formation of the solar system, right? So that's the kind of idea they want to keep you fixed on. Right. We don't want this idea that comets come from somewhere else, or they're formed by some other process which has little or nothing to do with the formation of the solar system.
Right. So is it suggesting that we had planets formed, and then maybe there was a massive collision which created loads of little bits, and they are comets. So comets maybe used to be part of a planet. Is that what it's suggesting?
Well, they're not suggesting that. NASA and the mainstream astronomers are not suggesting that.
Right.
It's several groups of people. One group is the David Tolbert and Wallace Thornhill, who've been working on the electric universe model since about probably for 10 or 15 years now. I first became aware of it in 2004. So they would contend that you can't say for sure that the comets are from the early solar system. They're not a result of leftovers of the early solar system. They think that at least a number of the comets, not necessarily all of them, are formed as a result of the breakup or partial breakup of planets in the solar system.
Right. All right. Now, just to come on to the electric theory of comets in the universe, let me just, because this is fairly new to me, some of the data that come back from these probes is suggesting that the comets have an electrical charge.
Right.
Just expand on that.
Right. So with standard astronomy, the solar system is electrically neutral. There's no overall charge, within the solar system, and there are no particular electrical interactions between the sun and the planets. It just doesn't happen. It's just all we have is basically heat exchange. We get heat from the sun, ultraviolet radiation, and so on. You get the odd bit of phosphorescence, like the aurora borealis, for example, is allegedly a kind of phosphorescence.
Right. And other than that, they're obeying Newton's laws of gravity and motion.
Yeah, and so the solar system is driven by the gravitational force, or that's been sort of morphed into relativity, which is slightly different. But essentially, gravitation still explains the motion of the planets in the solar system.
Describes, I would say.
Yeah.
Not explains.
Yeah, describes. That's probably a better word. So the idea that the electrical charge plays any significant role in the way that the solar system works, or in the solar system, or in the processes that go on in the solar system, that's generally regarded as just a sort of fringe theory.
Okay. So why did one of the probes? Why did the data suggest that there's some huge electric charge around one of these comets?
Well, one of the key missions was the 2005 mission to Comet Tempel 1, which was the Deep Impact mission. Now, what they did with the Deep Impact mission is they wanted to fire a projectile at the comet from a probe, and then film that projectile crash landing into the comet's nucleus and see what happened. And interestingly, as somebody pointed out to me when I was speaking about this, and I didn't really think about this initially, they actually fired a copper probe into the comet. And it makes you wonder why they chose copper as a material, which I think it was an £800 probe, and that's got to be very expensive to put £800 of copper. It's not. I mean, it's not beyond the realm of a space mission budget, of course, but it's still an expensive amount of copper, £800, to put into a probe to fire into the comet. Why was it copper? Why didn't they just use a lump of rock or something to see how the rock fragmented? But no, they chose copper. They probably had a reason for that. But what actually happened when they did that was, as this projectile approached the comet, and the projectile actually had a camera built into it, so they were able to film the approach to the comet, and they've got a time-lapse video of this, which is on their website, on NASA's website, and they basically saw a discharge, momentary discharge just before this probe impacted the surface of the comet, and the brilliance of the flash was probably 5, 6, 7, 8 times brighter, and all the NASA scientists were, wow, we didn't expect it to do that. This is much more energetic than we thought it would be. And also there was very little of a crater. There was hardly any crater. They claimed there was going to be a big crater, but there wasn't. Which, of course, if this thing was mainly snow and ice, an £800 copper thing travelling at, I forget the velocity, but it was several tens of thousands of miles an hour, would make quite a significant crater in a ball of ice. It wouldn't, because the heat from the impact would melt it, and all kinds of stuff would come flying out. That really wasn't seen, not to the degree that you'd expect. But the Electric Universe guys, particularly Wallace Thornhill, as the probe was approaching on the day, on the day that he knew that this mission was going to impact the comet, he said, he made these predictions, and he lists them on his website, and they said that there would probably be not only an electrical discharge momentarily before the probe hit. He also said that the electronics from the probe would experience interference because of the electrical charges.
Electric field.
Yeah, the electric field, exactly. And that's exactly what happened.
All right. Well, so if we've got a huge charged object flying through space at speed, that's what an electric current is. Something which has charge, which moves.
Right.
It is current.
Right.
So we've got kind of a current flowing through space then.
Right.
Really. So, and if that were to fly through a magnetic field, it will change its motion. We have, well, if the sun emits high levels of radiation, which it does, would that affect something which is charged?
Well, I don't think the radiation would, but you make a good point about the electrical field and the magnetic field. The sun has a magnetic field, so
right.
I don't know. I've not studied the electric universe theory to see if there are small perturbations in the orbit which are actually a result of the interaction between the electric field of the comet and the magnetic field. I don't think. You may find that the effects are not as strong as that.
Right. And what about the actual tail? Or do the electric universe people say that the tail is due to an electric effect?
Yeah, well, I think what they basically say is that obviously you're going to get some heating. Some of the effect does come from heating, but the fact that you don't have much water means that the way that the cloud is formed has to be explained in a different way. So the cloud is actually of the tail is formed probably by the electric fields of the object and the sun interacting, where you get the solar wind, which is a stream of charged particles. Those charged particles hit the comet, and they will charge the field around the comet and cause various effects, one of which is the formation of the tail, and that field helps to keep the tail contained in a particular shape in most cases.
Right. So have they not examined the orientation of the tail to say, well, hang on, that can't be purely but the result of a Newtonian reaction, that it's travelling at speed that way, therefore the tail would be immediately behind it? Does the tail deviate? Do you see what I mean?
Well, the tail can deviate because particularly this became particularly obvious with Hale-Bopp. I'm not sure if the Electric Universe guys have actually explained, for example, Comet Hale-Bopp. You can see that Comet Hale-Bopp has two tails, right. A gas tail and a dust tail. You can clearly see that if you go and look at the images. So it's quite possible that their explanation would involve the way that the electric field is formed around the comet, and that's what causes this.
Okay.
This.
Now I know that well, when I spoke to Lloyd Pye, he said that he was a fan of the Electric Universe theory. So why would it be that your average astronomer or cosmologist or physicist even maybe would reject the idea of forces due to electric effects in the formation of the solar system and the universe? What's the contention over it? Why is it such a hot potato?
Well, I'm not quite sure overall, but again, we could imagine that it's something to do with the way that we might derive energy. Right. Because if the solar system is more energetic in the sense of an electric field and so on, it may raise questions about various energetic processes that are going on in the solar system and having to have a different explanation for them. So that could be part of it. But I think it may in this case just be down to laziness. Right. In other words, if you realise that many of the fundamental sort of equations that have been worked out are actually they're only approximations and they're not accurate enough, right. Then you're going to have to rewrite a lot of the textbooks, and you're going to have to let go of a lot of the original research and replace it with something else.
Right. All right then, Andrew, we'll continue with the Electric Universe theory and comets after this.